So yeah, so what we ended up doing last time was finishing the central tendency. And then because basically everybody had left or didn't get the message that we'd be starting late, we stopped and we didn't do the spread measure. So today I'm going to start with spread measures, and then we will move on to the other parts of statistics. All right, so that's the plan. Yeah.
So anyway, that because I didn't do the homework for like the day that we missed because I was waiting to hear back from you.
Waiting to hear back from me.
Yeah, I emailed you, but I don't know if it got lost or.
Oh, I don't think I got an email from you. I would say, yeah, just email me again. I thought if I didn't reply, I usually reply to those, so I can't recall. So yeah, just talk to me afterwards and we'll see what's going on. So yeah, talk to me afterwards and we can get it situated. So just remind me. All right, so spread measures. So with central tendencies, we measure where the center of the group is. All right. And by center of the group, I really mean center of our data set. And now what we're going to do is we're going to measure spread, which means how spread out is our data set. Now, just like there's more than one way of finding the center of a data set, there's more than one way to talk about how spread out a data set is. Now, just as understanding, if you look at two sets of numbers, we'll call them A and B, and I ask you, well, which one is more spread out? It should be fairly obvious that A is more spread out than B. All of the numbers in B are closer. All of the numbers in A are more spread out. Another way to say that is if you look at these in numerical order, which they are in already, if you go from 0 to 10 and then to 20, there's a 10-unit jump between each number. Whereas if you go from 9 to 10 to 11, there's a 1-unit jump between each number. Okay. By the way, both of these have an average of 10 and a median of 10, both of these sets. So the center of each of these sets is the same. But as far as spread out goes, A is more spread out than B. If I get that. So we want some measurements of how to calculate and be more specific, not just based on intuition. All right. The first measurement of how spread out a set is a fairly easy measurement to calculate. It's the range. The range is simply the distance from the smallest number in our set numerically to the biggest number in our set numerically. And so to calculate the range, you just take that highest number and you subtract the lowest number, or you maximum minus minimum. Most people have seen range before. The one thing that I want to mention on range is that a range is a single number, okay? So if we look at set A, the range of set A we would take 20 minus 0 and get 20. So the range of set A is 20. And the range of set B we would find by taking 11 minus 9 and get it 2. All right. By the way, some people will write range equals 9-11. That's not the range, right? The range is the numerical value of 2 or the numerical value of 20. If I get that. So it's not from this to that. The range is a specific numerical value. Let's take a look at this set. This is a set we've dealt with before. We found the central tendencies of this set. This was the set of salaries. Let's look at the range for this. Well, the smallest number in this set is 35,000. The biggest number in this set is 237,000. So we're going to take 237,000 and subtract 35,000. Okay. And that means the range is 202,000. So the actual range is 202,000. By the way, if you wanted to put a label on that, the range is $202,000 technically, because all these things were measured in dollars. Okay. Now the range is a fine measurement to talk about, very quick and easy to calculate. But the downfall of range is that it only cares about the very biggest number and the very smallest number. So if these in-between numbers are more or less spread out, it doesn't affect the range. So this is sort of the impetus to find a new measurement of how spread out a set is. And that new measurement is called the standard deviation. Now, what I'm giving you here is something called the population standard deviation. It's the only type of standard deviation that we're going to look at. Okay, there's also a sample standard deviation. But we're just going to calculate the population standard deviation in this class. And what the standard deviation does is it takes and calculates how far a set is from a constant set, and then we're dividing by the size of the set. Technically dividing by the square root of the size of the set. All right. So the standard deviation is the distance from our set to a constant set. Again, and then it's normed by dividing by how many items are in our set at some point. it's in mathematics, when we have the population standard deviation, it's always denoted by this lowercase Greek letter sigma. Right, that's a lowercase sigma. And what it tells you to do is take a big square root. It takes every data point, every number in your set, and it subtracts the average and squares it. And then it adds up all of those. And then it divides by n. So basically, we're calculating how far each individual data point or each individual value is away from the average. Some of those will be under the average, some of those will be above the average. That's why we square it so that everything turns positive. Add those things up, divide by n, and then to sort of almost undo those squares, we take a square root. That doesn't undo each individual square, undoes the. Now, let me explain kind of how this works with an example. All right? And kind of, let's say we have a set which is just two numbers, 3, 7. Okay. The average of that set, the mean, add 3 and 7 divided by 2, you get a 5. So the average is 5. What the standard deviation does is it basically says, how far is this set from the set 5, 5. Now, the reason I take 5, 5 is because that is the set with the same average, which is constant, meaning every entry is the same. Does that make sense? So it's like saying, what's the closest to this thing? The closest constant set to this one is this one, right? Because it has the same average, it has to be the closest. And so we start by saying, well, how far is 3 away from 5? 3 away from 5. And then how far is 7 away from 5? And then we divide the whole thing by 2, and then take a square root, and that would give me my standard deviation. That makes sense? Square each piece, divide by 2, take a square root, that'll give you your standard deviation. Now, I want to compare that to figuring out the distance from 0.37 to the constant point of 5, 5. right? So imagine we have the point 37. And I want to figure out how far away is that from the point 55. What's the length of that line? Well, one way I could do it is by drawing a right triangle. Hopefully you know that on a right triangle with legs A and B, I'll call that D for distance, that the hypotenuse squared is equal to A squared plus B squared. That's the Pythagorean theorem. So the distance from this point to this point, or from this point to that point, is the square root of A squared plus B squared. All right, that's just the Pythagorean theorem. Now, what is A and what is B? Actually, I should have probably, let me do it this way. A, B, can I do that? No problem. Right, which one I call A, which one I call B? Well, A is the change in the X values. So if I measure A goes from the X value of 0.2 down to the X value of 0.1. So it's like 3 minus 5 or 5 minus 3, whichever way you're subtracting. I'm going to do a subtraction of 3 minus 5. That's your A. And then the B is the change in the Y values. From 7 to 5 or from 5 to 7, depending on which way you subtract. I'm going to write 7 minus 5 in there. Notice that's basically identical to the numerator here. The only difference between the distance between those 2 points and the distance between 2 sets is that at some point I've divided by 2 because there's 2 elements here. And when you get to more and more dimensions, you want to divide by the size of the set, just as a standardization factor. Does that make sense? So standard deviation is essentially like a distance. It is a distance, all right, with a norm of how many elements are in your set, sort of averaging out how many elements in your set. So in one sense, not exactly this, but it's kind of like almost like the average distance. It's not exactly that, but it's a distance between two, just like a distance between 2 points, right? So that's what it's doing. Again, we have a division by 2 here, where we don't over here, but that's the basics of it. All right. So let's try an example. Let's try 2, 6, 10. All right. We'll find both the range and the standard deviation of the set 2, 6, 10. And then on the next example, I'll show you why the division by n exists. So we have the set 2, 6, 10. There you go. By the way, this has a mean. If you add up 2 plus 6 plus 10, you get 18. Divide by 3, you get a 6. So the average there is 6. So if we're looking for the standard deviation of that set, you know what, let me do the range first. Range will be quicker, right? Range is pretty easy. Range is the distance between the highest value and the lowest value. So the range is 8. Standard deviation, we're gonna take each value and figure out how far away from 6 it is, and then square that number, and then add them all up. After I add those all up, I'm going to divide by 3, and then I'll take a square root of the whole thing. Now, what I usually do is I usually just put the numerator in my calculator first. I usually just write 2 minus 6 in parentheses, squared, plus 6 minus 6 squared, plus 10 minus 6 squared. In my case, when I did that, I ended up getting a 32. So the standard deviation is going to be the square root of 32 over 3. Okay. And then I usually just type this in because Moodle's going to ask you to give your answer rounded to 2 decimal places. Okay. But oftentimes, if you try to type it in here, there's just so much going on to try to make sure that everything gets under the square root. It turns into ugly things. So I usually calculate the numerator and then type this in. And when I type this into my calculator, square root of 32 divided by 3, I ended up with about a 3.27, roughly. So we all got good. So there you go. That's your range of that set, and then your standard deviation of that set. Now the next example does this. It says, what if we have a different set? And all we did was put in extra 6s. 2, 6, 6, 6, 6, 6, 6, 10. Obviously, if we just put in extra 6s, our average is still going to be 6, right? And our range is still 8. I want you to, on your own, calculate the standard deviation. Alright. Now you have to be careful about typing this in your calculator, but the basic idea is you take each one of these numbers, subtract the mean, and then square them all. After you do that, you add up the numbers that have been squared. By the way, if there are repeats, in general, you have to, add them, each of the repeats up. Although 6 minus 6 is 0, so that's not going to contribute much, right, on all of these. After I add those all up, I'm going to divide by 5 and then take a square root. Now, like I said, what I tend to do is I tend to type in my numerator. In this case, my numerator comes out to 32 because that's 4 squared, that's 0 squared, 0 squared, 0 squared, another 4 squared. So 4 squared plus 4 squared, essentially. And that becomes 32. 32 over 5 is underneath my square root. And when I type that into my calculator, I get 2.53, roughly. It's obviously I'm rounding to 2 decimal places, which is what Moodle's going to ask you to do. Now I put these two back to back so that you can kind of see what the effect of adding more numbers does. In some sense, this is a little bit more spread out because there's a lot of middle numbers here, right? This is taking into account all these middle numbers, which happen to be right on the mean. So in some sense, this is a closer set to a constant set because only 2 of our numbers are different than the mean out of 5. Whereas here, this is a little bit further from our constant set because it's 2 out of 3 numbers are different from our mean. Okay. So that's the effect of this division by the size of the set, in other words. Okay. Now, if these numbers happen to be not 6s, if this number was like a -8 and this number was like a 42, then obviously the standard deviation would be a lot more than this. So that's the idea. Now we can do the same thing with any set that we choose. So even if I want to take this set I could find the standard deviation of this set. Now, just so that we're all on the same page, this is going to be some big numbers to type in your calculator. That's okay. The average of this set for the salary the mean, we calculated this previously, it should be 83,500. Okay. So what I'm going to do to find the standard deviation is I'm going to take each one of those numbers, 38,500, subtract 83,500, square it. Then I take 35,000, subtract 83,500. Oh, oops, I miswrote that. Let's put 35. Square that. I gotta mute this because I'm not gonna have enough room otherwise. All right. Let me write the data sets. So 45,000 is my next number. So I take 45,000 minus the average or the mean, square that, plus 237,000 minus the average, square that. And then the last number was 62,000 minus the average. Square that. We divide that whole thing by 5. And then we take the square root of that whole thing. Now I'm going to try to type this in accurately into my calculator. 38500. Plus, in parentheses, 35,000. Make sure every time you're putting in the correct parentheses and all of that. Now my calculator, this is such a big number that it gave me the number in scientific notation. All right. My calculator, it said 2.9884 and then E10, which means times 10 to the 10th power. Okay. By the way, that's fine to use. On my calculator, I'm just going to hit divide by 5 and then take a square root of that answer. All right. Which you can do if you want, or you can do a square root of the answer over 5. And what I got is approximately 77309.77. By the way, remember all of our measurements were in dollars. So technically, the standard deviation is also in dollars. That's standard deviation of $77,309.77. Is that okay? Again, it's a lot to type in your calculator on this line, right? And in reality, this is a data set with only 5 entries. You can imagine trying to do something like this by hand if your data set had 50 entries, right? And my average was pretty nice whole number, your average could be some ugly, decimal number. So you can envision worse scenarios than this. This is as bad as it gets in here, all right? In here, we're not gonna be working with data sets that are huge. And our averages should be fairly nice. Okay, for standard deviation calculations. And the reason why it's fairly nice in here is because if you're actually doing this, if you're actually doing statistics in a real way, most times you use computer programs to calculate these things and generate these things quickly, all right? We'll hopefully take a look at Excel and how Excel can do that. A bit later, all right, like next class period, all right? So obviously, if sets get bigger, if numbers get uglier, we're gonna use some sort of a computer program to calculate those things. But we know how to do it by hand on smaller sets. The other thing that I want you to do is build a little bit of intuition about how spread out a set is. So if you look at these two sets, A and B, A goes from 10 to 20 to 30 to 40 to 50 to 60 to 70. And then B goes 1, 2, 3, 4, 5, and 6. Which one is more spread out? Which one do you think is going to have a bigger standard deviation, in other words? A, right? The gaps between the numbers in A are gaps of jumps of 10s. Whereas the gaps between the numbers in B, jumps between numbers are all 1. And so A is going to have more standard, higher standard deviation. More deviation, I just mean standard deviation, higher standard deviation. So set A is going to have a higher standard deviation. Now, what if we have the same A, but now B becomes 310, 320, 330, 340, 350, 360, 370. Which set now is going to have a bigger standard deviation? Yeah, since the jumps are the same size, the standard deviation is also going to be the same size. All right. So in this case, A and B would have the same standard deviations because the jumps between the numbers are all the same size. All right, they're all 10s in A, jumps of size 10 in B as well. That makes sense? So you can kind of intuit which one is going to have more standard deviation without even having to calculate the standard deviation in these cases. Is that right? Good. All right. So that's the basics of spread measures that you should know. Like I said, I'll probably next class period get into a couple little features in Excel that you can use. But what I'd like to do now is start into the manipulating statistics part.
I'm gonna send me an email.
Okay.
Just make sure.
Yeah, that'd be good. Yeah, make sure it's JD Webster at
Okay.
Admission. Yeah, yep.
Thank you.
So what I mean by manipulating statistics is we're going to look at results and how statistical studies can be misused. All right? Sometimes that misuse is done on accident, and sometimes that misuse is done on purpose. So we have to be a little bit skeptical of things that we see, or we have to be a little bit wary about results from studies, because sometimes studies can get it wrong. Now, when I say skeptical, I'm not saying that we think that everybody at all times is trying to throw us off. You know, there's some secret agenda behind every study. I'm not saying that. And I'm not saying that every study we don't like, we should scan with a fine-tooth comb just so that I can dismiss results of studies that I may not like, right? Those are both very common ways of thinking, but we don't want to do that here. We don't want to think that everything's been manipulated. And all I'm saying here is that we need to be skeptical in the sense that we need to realize what could go wrong with studies and with data sharing. All right? So we're going to start out looking at some things that can go wrong with studies. And then we'll look at some ways that we can manipulate the way people see results in the second part of manipulating statistics. So in this part, I want to look at some things that can go wrong with studies. So let's say I'm a researcher and I want to research some phenomenon. We got and I want to design a study. Okay. Well, one thing I want to do when I design a study is I want to avoid suspect samples. A suspect sample just means a bad sample. All right? It's a sample that doesn't represent the population that I'm looking at. So my example is saying, well, what if I want to find the average height in the United States? So let's say I wanted to find the average height in the United States. And I said, well, you know what? The NBA publishes all their heights. So let's just use the NBA heights on their players, NBA players' heights, to represent a good sample of heights of human beings in the United States. I hope everybody can see why that would be a bad sample. All right? The heights of people in the NBA are exceptionally tall compared to the rest of the population. Right? So if you were looking at heights and your sample was NBA players, that would be a bad sample. Wouldn't represent a bigger population. Okay. The same thing, if you did a study on how many books people read a week, and you put up a table, a polling table, and you put that table in front of a library, you might say, well, this is where people, go to read books or whatever. They'd say, yes, but if you put your table in front of a library, that doesn't give you a good sample of everybody in town because there's probably a lot of people who don't frequent the library. That makes sense? So you don't get as many people who say 0. All right. So how many books a week or how many books a year do you read? Putting that surveying people who go to the library would be a bad example. So we don't want suspect samples. We want to avoid samples. And we've already talked about sampling techniques that work, like doing random samples or systemic samples or cluster samples, or the one that's not scientific, which is convenient sample, right? So we've already talked about how to get good samples, and I'll just leave it at that. So suspect samples are bad samples. Another thing that is very common is that people will often do a study and they will leave out an important variable. If a study leaves out an important variable, that variable that is left out is called a lurking variable. All right. There have been a lot of different studies done, and a lot of these get reported in the media and then get criticized afterwards because the media says, oh, I found this research project that linked this thing to that thing. And they've left out a lot of lurking variables, okay? Here's one that was published. So the study linked smoking, or it might have been parental smoking, I think. So in other words, do your parents smoke with college graduation? And found that if your parents smoked, you had a lower percentage of graduating from college. If your parents didn't smoke, you had a higher percentage of graduating from college. So the study was like, well, the graduating from college must have something to do, must be linked to the smoking. And it was widely criticized because they left out a lot of lurking variables. That would maybe impact college graduation, and maybe also that might be subtly linked to smoking in different ways. All right? Things like parental income. Or what schools or what area you live in. So what area did you live in? What school did you attend? And by the way, school, I mean high school, did you attend? All right. It turns out that at poorer high schools, more people come from low income backgrounds, and more of those low income backgrounds smoke. And therefore, it would be kind of all, it might not be the smoking that's causing low graduation rates, but what school, high school you attended, and what are your parents' income, right? Because some people might not have the income to, and might not want to take out student loans to graduate from college, right? Those types of things. Everybody understand lurking variables? What's going on there? We're saying those are variables that are left out of this study, but are still important. Still would impact this study. And impact it in significant ways. All right. Now, another thing that could go wrong with studies is if we're doing polling, if we're asking people questions, questions could have bias. All right. So question bias is when that sort of the way you ask the question can lead to different answers. Now, when I say it can lead to different answers, I don't mean everybody's going to answer different. But if I walk up to you and say, is such and such person a good person, or is such and such person a bad person? Okay. Even the fact that I put in the word good and bad could bias the question, right? And it could be especially biased if I put in some adjectives, some colorful adjectives. So for instance, the president of this college, the president of MID, is President Hood. Okay, his name's President Hood. And if I said, do you think the nice and fantastic President Hood is doing a decent job at leading the college? Obviously, those colorful adjectives at the beginning would bias it in one direction. And if I put in negative adjectives, like, do you think the awful and terrible President Hood is doing a good job at the college? That would bias it in the other direction, right? But there's also really subtle ways to influence the way a question comes out. One of the more famous historical examples is the following. Let's ask a question about tax code policy in the United States. Should the federal income tax rate be raised for rich people. Or let's just cross out rich people and say billionaires. All right? So I ask a question like that. Okay? And then I could ask a very similar question that got to the same idea. What should the federal income tax rate be for billionaires? Okay. Notice the different questions. This question, the one I wrote in red, basically asks for a yes/no answer. Should it be raised? Either yes or no. It turns out, by the way, most people will say yes to this question. All right, majority of people say yes to that question. When they ask, well, what should it be? Most people, well, you have to give a numerical answer, right? By the way, this is historical. This has been true for lots of things. So income tax rate should be raised for billionaires. Most people say yes. What should the income tax rate be for billionaires? Most people say about 25 to 30%. Okay. Now, what's the issue with that? Well, the issue with that is that we looked at tax brackets earlier in this semester. The highest tax bracket on income taxes, this is, again, remember, income taxes, is already at 37%. So a lot of people, therefore, would have said, yes, raise it to something that it's already lower than. Does that make sense? So even doing these subtle things of asking yes/no questions versus asking percentage type answer questions can give you different results. Does that make sense? And probably the same thing would be true of if you ask, for instance, do you approve of the job that, you know, president of this college is doing? Yes, no. And then if you ask something like, if you rated the president of this college based on a scale from 0 to 10, what would you rate the president? Okay, those would give you maybe slightly different answers. And so those different subtle ways of asking questions are very important to understand. Okay. Now, since I'm talking about asking questions and polling people and all of that, we can't ignore that oftentimes the people who you're asking questions to will tell you misleading information themselves. Maybe not on purpose, but they do. There are certain types of questions you can ask people, especially if you ask them to self-diagnose something, that they're going to give you essentially errors for. Let me give you two examples, and these are well-known examples. If I ask people how many calories they eat in a day, almost everybody underestimates the number of calories that they consume in a day. Does that make sense? The vast majority of us underestimate that number. Don't add it up correctly. The same thing would be true if I asked the question I talked about earlier, how many books do you read in a year? Most people would overestimate that, right? Because we usually think of, ourselves, or we want to see ourselves in the positive light. So when we say, how many books did you read in last year? A lot of people will overestimate that number. How many calories did you eat? Well, I want to be thought of as being healthier than I really am, so I'll underestimate that number. Okay? So you do have to be wary about pulling data where people are telling you things like that. I saw, this was on some political, I can't even remember what it was. It was some sort of a YouTube video, but they were talking about some poll, and I almost laughed at it because they said, well, yeah, the people said they were voting because of this reason, this reason, this reason, right? And I'm like, those are, not that those are bad reasons to vote for an individual, but it was one of those things where, well, yeah, they say they're voting for reason A, but could they actually be voting for the individual because of reason B, right? And so, yeah, they're saying they're voting for reason A, but they're actually voting for reason B, justifying it in their head. That makes sense? All right. So those are ways that studies can go wrong. Now, the one that I'm going to be highlighting again is the lurking variables. These happen all the time because a lot of times researchers don't really know what they're doing statistically. And they'll take two variables, look at nothing else other than those two variables, and say, yeah, they look to be interconnected somehow. And if you look at two variables and see if they're interconnected somehow, that's usually a red flag for there being lurking variables somewhere else. Okay, that's probably the biggest one. Okay. Now, in the last few minutes of class, I'm going to briefly talk about more ways to manipulate statistics. And these are ways that we can manipulate the way we talk about the data. So let's just, for the sake of argument, say I collected my data right. I have good samples, so no suspect samples. I looked at all the lurking variables and assessed all the lurking variables. right? I asked the unbiased questions in a way that didn't give me any responder error. Or maybe none of that applied. Maybe I'm just looking at a data set and I'm saying, look at these facts on the data set. Well, we can still kind of manipulate how people see our data or how people see our results by the way we show the data to those individuals. All right. Now, the example that we already saw was choosing our measures of central tendency. Remember back last class period, we saw that the salary data set had a median of $45,000 and had a mean of $83,500. And it had no mode. So our median was 45,000, our average was 83,500. Now, if I choose as a researcher to publish my data and I use and keep referring back to the average salary, that's going to give people the impression that the data set has higher salaries compared to if I would have used the median in all of my referencing back to the data set. Does that make sense? So if I keep using the mean over and over and over when I reference back to the data set, and somebody else uses the median value when they reference back to the data set over and over and over again, people who are reading my work are going to assume we have average salaries that are higher compared to people reading the other person's work are going to assume those salaries are lower, right? So by choosing a central tendency, which is a bigger value, the reader assumes the data set has bigger values. And by choosing the central tendency with the lower value, people think that the data set has lower values. That makes sense? So which central tendency I want to publish can affect how the readers see the data set. They can see the data set as higher values or lower values based on the central tendency that I publish. All right, and describe the data set with. All right. Another thing that's real similar, although not dealing with central tendencies, is something called changing the subject. Now, changing the subject isn't that I start talking about a new subject, okay? For statistics, the concept of changing the subject means I'm changing the way I'm measuring. The most common way to do this is to talk about raw numbers versus percentages. in order to make my number sound bigger or smaller. Okay? And there's lots of examples of changing the subject. So one way to do it is to talk about, well, let's talk about like government spending on some program. Let's say that the government decides to spend $20 million on a program. Okay. Now, the people who want to have that money spent might refer to that $20 million in spending, and they'll say something like, well, we're going to spend 0.02% of a budget on a government program. These might be the same numbers. Okay? You know, let's say they spent 0.02 of the Pentagon's budget on some program. And somebody else might say, well, you spent $20 million on that program. Well, 20 million might be 0.02% of the Pentagon's budget. Does that make sense? That's, I mean, a lot of these government agencies have gigantic budgets, okay? Compared to like an individual budget, compared to somebody like me, right? And if you want a number to sound smaller, in this case, you use the percentage. If you want that number to sound bigger, you probably use the raw number in this case. Everybody get that? So because $20 million to you and I, that's a gigantic amount, right? Like if you gave me $20 million, you'd definitely get an A in this class, for sure, right? A lot of money. But when you hear 0.02% of a budget, that doesn't sound very big. Now it could work in reverse as well. You can say there was a 200% increase in deaths via, I don't know, disease X, we'll just call it. All right. In the US, let's say. Versus there were only 2 extra deaths via disease X. A 200% increase sounds scary, right? That's a gigantic increase. But if that 200% increase means you just went from 1 death last year to 3 deaths this year, probably not that big of a deal. Not something to lose sleep over. In a country of, you know, like the US, we have over 300 million people. It's like 340 million or something like that. 3 deaths by a certain disease is not really cause for worry. You know? Does that make sense? So 200% increase versus 2 extra. In that case, the percentage sounds like a really big increase, where the raw number sounds like a really small increase. And that's the opposite over here. Okay, so that's what changing the subject is all about. And there are other ways to change the subject as well, to just talk about a certain type of data in different ways. Okay. Percentages versus raw numbers is the most common. All right, I'll stop there, and next time we'll finish this up, and we'll finish up all the rest of the stats stuff. That work? All right, I'll see you all next time.